Good afternoon. Good afternoon, and welcome to another lecture of electronics in which we were trying to study semiconductors. Yesterday, in the last class, I have told you what are semiconductors. So we'll start with the same. Uh, Let me introduce myself. Myself, Dr. N.D. Mishram, Head and Associate Professor, Department of Electronics, Sri Mathura Das Mohta College of Science. I guess my screen is visible to you, and you are able to view my screen, my presentation, right? So we were studying semiconductors. In the last class, we have studied these semiconductors. But in the last class, I have told you something which is very important for the semiconductors. That is, what is the difference between the conductor, insulator, and semiconductor. So we'll try to recall the same in this presentation too. So as I've told you, these are semiconductors. These are some materials, some devices which are being made by using semiconductors, LEDs and transistors and ICs. What is a semiconductor? I have told you, which lies between the conductor and the insulator, is called as a semiconductor. These are the things which are being manufactured by using semiconductors, right? So those are semiconductors. These are capacitors. These are not semiconductors. The elements, group 4 elements of the periodic table are called as semiconductors like carbon, silicon, germanium, and these all. And these yellow materials are basically concerned of using those in semiconductors, right? So we are going to use these group 3 elements also, and group 5 elements also, phosphorus, arsenates, and these, then boron, aluminum, gallium, indium, ये सब हम लोग यूज करने वाले हैं सेमीकंडक्टर्स में. And what is the range of conductiveness? I have told you yesterday that semiconductors are less conductive than metals, and say more conductive than insulators. Insulators are does not conduct, so their conductivity is zero, whereas metals conductivity is infinite. Semiconductor lies in between. So this is being shown in this graph, right? So that is the range of conductiveness. The semiconductor falls somewhere midway between conductor and insulator. I have told you yesterday in the lecture. Yeah. So this is what it means of conduciveness. If you connect a copper in between that, the current flows through that copper. Even through glass, it does not conduct. So only steel, metals, or good conductors of heat and electricity pass current through them, and that is being shown in this say in this uh, clip, right? So when you attach steel, then the right light will glow. If you attach wood, then the light will not glow. If you attach copper, the light will again glow. If you attach glass, then the light is not glowing. So glass and wood are bad conductor of electricity, whereas copper, silver are good conductor of electricity. So semiconductors have special electronic properties which allow them to be insulating or conducting depending on their composition, right? So I've told you this, how they are behave as that. These are the persons which have started. This is some history of that. We won't go in depth. Uh, so yeah, these are some of the things. Yeah, this is what we have discussed yesterday. So we are having two bands, conduction band and the valence band, and this is the energy. So, and this is the band gap, right? So the electrons in the valence band jump into conduction band, and they play a vital role in conductivity. So that is this principle of that. This is valence band. What is valence band? The highest occupied energy band is called the valence band, where the electrons are there in its last outermost shell, right? So most electrons remain bound to the atoms in this band. And what is a conduction band? The conduction band is the band of orbitals that are high in energy as compared to valence band and are generally empty. They are empty, right? So there are no free electrons in the conduction band. But when the valence band electrons gain some energy and they jump into conduction band, right? So it is the band that accepts the electrons from valence band. Good. So conduction band, and this is the energy gap, and this is what I yesterday told you on the board, right? So the leap required for the electrons from the valence band to enter the conduction band, that is to jump from this valence band to conduction band. And this is what I mean to say by a conduction band and valence band. So if you say this is the valence band over here and this is a conduction band, so you need some energy to jump from this position to this position, and this particular is called as the conduction band, right? So these are the conductors. What are conductors actually? They are having many free electrons in for conduction, and that is why they are called as conductors. So in conductors, electrons can move freely among these orbitals within an energy band as long as the orbitals are not completely occupied. So the electrons are free for conduction, and therefore the material behaves as a conductor. Conductor means which conducts heat and electricity, right? And this is a band energy gap. Conductors की नहीं है ये, बस दिखा रहे हैं. So this is actually the concept. The valence band is completely empty. Uh, like this. Nine. Yeah, this is the graph. So we are having the overlapping of conduction band and valence band. So there are many free electrons for conduction, right? So overlap permits electrons to freely drift between the bands, and therefore there are many electrons for conduction. Also in conductors, the energy gap is non-existent or relatively small. तो कभी रहती है, कभी नहीं रहती है. Maximum times it overlaps, right? Whereas in insulators, the band energy is very high. In insulators, the valence band is completely filled, right? It is completely full, and the conduction band is completely empty, like this. So we are having a traffic jam over here. It shows that there is no space for electrons to jump, right? So this is and the energy gap, the band energy gap or the forbidden energy gap is very high. So the electrons cannot gain that much of energy to break the bond of the atom and jump into the conduction band. Uh, so therefore, it behaves as an insulator. It does not conduct heat and electricity. So also in insulators, the energy gap is relatively large. Whereas in semiconductors, the band energy gap is very small. The valence band is full, but energy gap is intermediate. So there might be some electrons which can gain energy and they can jump in conduction band, and the material behaves as a conductor. Whereas at absolute zero temperature, uh, the valence band is completely filled and conduction band is completely empty. So what happens? There are no free electrons for conduction and it behaves as an insulator. So in certain temperature like absolute zero, the semiconductor behaves as an insulator, whereas at room temperature it behaves as a conductor. So this is the uh, diagram. I guess you have understood. Semiconductors, conduction band and energy gap. Only a small leap is required for an electron to enter the conduction band. Right. So for that, uh, yes. So the energy gap is very small, and the valence band electrons can jump into the conduction band. And these are the say say the difference between the energy band gap of metal, semiconductor, and insulator. As I have told you, taught you, like in metals, the conduction band and valence band overlap each other, and therefore there are many free electrons. Whereas in semiconductors, this is, forbidden energy gap is very small, so might some electrons jump into conduction band and it behaves as a conductor. Whereas in insulator, the energy gap is very high and the valence band is completely filled, whereas conduction band is completely empty. So there are no free electrons to take participation in the conduction, right? So therefore, this type of material behaves as an insulator. So this is the diagram of that. Sorry. Uh, my presentation, I guess I missed that presentation. Wait for a moment. Uh, yeah, I guess it is visible. So yes, so these are the materials. Silicon is the main material which is having the property of a semiconductor. And what is the say? What is the importance of that? So silicon is having four electrons in its outermost shell. and therefore it behaves as a semiconductor. So it requires four more electrons to make covalent bonds with the neighboring atom, and therefore it behaves as a semiconductor. So it is having the number of electrons as 14. So 2, 8 is the 2 is the first orbit, and 8 electrons is the second orbit. And in the last orbit, that is the third orbit, it is having only 4 electrons. So as you can see, the atom of the say the atom of silicon will make four covalent bonds with the neighboring four atoms, and it will saturate itself, and it will complete its outermost shell, and thus there are no free electrons at absolute zero temperature. So this is the basic concept. So this is how the silicon crystal appears. What is a silicon? So silicon is very common element, and the main element is in sand or in quartz. So in sand we get silica in abundance. So silicon is in abundance in say these sands. So it is abundantly present, and then it is also present in the quartz crystal, silicon, and we call it as silicate, right? So silicate dioxide, that is sand. So, and this is the arrangement of silicon. So as I told you that in center it is having a nucleus. In the first orbit it is having 2 electrons, and in the second orbit it is having 8 electrons over there. So total 10 electrons in this, and this forms the core. So this forms the core of the atom of a silicon, and 4 electrons are in the outermost shell. So this silicon atom requires 4 more electrons to complete its last orbit. So what it does, it forms, it shares 1 electron with the neighboring atom like this, and it bounds 4 atoms in its vicinity. So it will make this 4 electrons, it will share these 4 electrons with the neighboring 4 atoms, and it will form four covalent bonds, and thus silicon atom is saturated, right, like this. So this is the combination of that silicon crystal. So it is making four covalent bonds with its four neighboring atoms. I will show you that on board also. So this is the silicon crystal, right? So the four covalent bonds are formed with the four neighboring atoms, and there are no free electrons for conduction. So this is the concept over there. So it is having uh, अच्छा. So on that note, we are having two types of semiconductors. One is called as intrinsic semiconductor, and the other one is called as the extrinsic semiconductor. A silicon crystal is different from an insulator, as I told you. Acha. There are two types of semiconductor: intrinsic semiconductor and extrinsic semiconductor. Intrinsic semiconductor is a semiconductor in its pure form, means when we are using the same type of a material to form a crystal, then it is called as the intrinsic semiconductor. It means that if you are using a silicon, then all the bonds are going to be made, or all the crystal is in its pure form, and there are only silicon atoms. So if it is so, then that particular crystal is called as the intrinsic semiconductor. That is called as the intrinsic semiconductor. And if some amount of impurity is added to this pure crystal, then it is called as extrinsic semiconductor. So extrinsic semiconductor is an impure crystal, whereas intrinsic semiconductor is in its pure form. I guess you have understood the definition. Intrinsic semiconductor means a semiconductor in its pure form, means we are not going to use uh, we are not going to use any other impurity in that crystal. So that is why it is called as a intrinsic semiconductor or a pure semiconductor, right? So that is an intrinsic semiconductor, a semiconductor in its pure form. Again, I'm repeating it. A semiconductor in its pure form is called as intrinsic semiconductor, right? So this is the intrinsic semiconductor over there. And if you are able to see, uh, at absolute zero temperature, there are no free electrons for conduction, right? So at absolute zero degree temperature, all the four electrons are making four covalent bonds with the neighboring four atoms, and therefore there are no free electrons for conduction. But at room temperature, due to thermal vibration, remember this word, due to thermal vibration, some of the electrons may gain thermal energy due to vibration, and then it can jump into conduction band, right? So due to that, a small current flows through this pure silicon crystal. So at room temperature, it behaves as a conductor, whereas at absolute zero temperature, it behaves as an insulator. So that is why it is called as a semiconductor. Means at some temperature it behaves as a conductor, at another temperature it behaves as an insulator. So at any temperature above absolute zero temperature, there is a finite probability that an electron in the lattice will be knocked loose from its position, right? So uh, uh, what I said, due to thermal vibrations, right? Due to thermal vibrations, some electrons may gain energy and may break the covalent bond and may participate in the conduction. Therefore, it is called as a semiconductor, and it behaves as a conductor when above the absolute zero temperature, right? So this is how it goes. So what happens? Uh, some of the electrons may make free from this covalent bond and jump into the another form, and then it will take participation in the conduction, right? So these are the free electrons over there, and these are the holes. The concept of holes I am going to tell you. The electron in the lattice knocked loose from its position leaves behind an electron deficiency called as a hole. I'll tell you this. The absence of electron is called as a hole. Where there is no electron present, that is called as. It is an imaginary concept, right? So if there is no electron at a place, if there is a blank space, or if there is no electron at a space, or if some electron jumps from its own original position to the other position, then that left blank space is called as a hole. That is the concept of a hole. If electron jumps from this, so automatically a positive polarity comes on it here. So and if an electron jumps to another atom, then automatically negative polarity comes over here. So this is the basic concept of a hole. I will let you know in the next coming lectures, right? So this is a silicon, and this is the formation of say a crystal. So when a potential is applied on a pure silicon or an intrinsic semiconductor, so what happens? Some of the electrons may jump, and if you are able to see over here, the current will start flowing from this. So this is a battery which is connected to a pure intrinsic semiconductor crystal, and as I've told you, some electrons may gain energy, and the holes will travel in this direction, whereas the electrons will travel in this direction. So the current will flow from here, from the positive terminal to the ground, right? So this is the conventional current that is supposed to be flown from this semiconductor, and we call it as the material is behaving as a conductor. So the current flows through a intrinsic semiconductor, but not at absolute zero temperature, but at above absolute zero temperature or at room temperature. So if a voltage is applied, then both the electron and the hole can contribute to a small current flow, right? So this is the positive potential, positive terminal of a battery is connected to this semiconductor, and this is a negative potential. So negative terminal of a battery is connected to the side, and the current always flows in the opposite. The flow of electron is always opposite to the flow of current, right? The current flows from positive terminal to negative terminal, positive terminal to ground, right? Whereas the electrons flow, if you are able to see over here, the arrow has been shown over here. The electrons are moving towards the positive terminals. As electrons are negatively charged, they are expected to move towards the positive terminal of the battery, right? So this is the movement of the holes from left to right, and the movement of electrons from right to left, right? That is being shown in this. So this pure intrinsic semiconductor behaves as a conductor, right? It behaves as a conductor. But at absolute zero temperature, there are no free electrons, since they don't gain any energy, and they not take participation in the conduction. Therefore, at absolute zero temperature, the same intrinsic semiconductor behaves as an insulator. So at some time it will behave as a conductor, at some time it will behave as an insulator, right? So this is the flow of current, and this is the impurity which is supposed to be added like this. So I will tell you. So this was about the intrinsic semiconductor, and for a extrinsic semiconductor, whenever certain amount of impurity is added to a pure semiconductor, pure intrinsic semiconductor, then it becomes extrinsic semiconductor. Remember this: when a small amount, or when an amount of impurity is added to a pure semiconductor, it becomes extrinsic semiconductor, right? We are having two types of semiconductors: intrinsic semiconductor and extrinsic semiconductor. Intrinsic semiconductor is in its pure form, that is called as intrinsic semiconductor, whereas the impure form of a semiconductor is called as the extrinsic semiconductor. Right? So when a certain amount of impurity is added to a pure intrinsic semiconductor, then it becomes extrinsic semiconductor. Now these are impurities which are being added. Now let us see. So this is there is one more concept that is called as doping. Doping in this formation is called as mixing or adding an impurity. Mixing or adding an impurity to a pure intrinsic semiconductor, that is called as doping. So doping is just mixing of a impurity, right? So doping is adding an impurity or mixing of an impurity to a pure intrinsic semiconductor uh, to that note, that is called as doping. Now, on that note, we are having two types of impurities to be added, and will be having two types of extrinsic semiconductor. What are those? Let us see. So, we are having this P type of a semiconductor when boron or gallium, that implies that in their outermost shell they are having three electrons, right? So, trivalent impurity. Whenever a trivalent impurity is added to a pure intrinsic semiconductor, then it becomes a P type of a semiconductor. Now let us see how it goes. So P type doping is boron and gallium is a dopant, and yeah. So here, if you are able to see that we are having this in group three elements, means we are having the trivalent impurity. That is, it is having three electrons in its outermost shell, right? So whenever we dope this pure semiconductor with a trivalent impurity like this, so whenever we dope like this, so what is the ratio of doping is 1 is to 100, means one impurity and 100 silicon atoms. So we are having 100 silicons and one impurity, that is one boron. So if you add like that, then this is the structure which is formed on it. So we are able to see that boron is in the center and four silicon atoms are along that sides. So what happens? Three electrons of boron will make three covalent bonds with the neighboring three silicon atoms, and one space is left. This left space is called as a hole. Where there is missing of an electron is called as a hole, right? So as you are able to see, the boron is having a trivalent impurity. If it is added in the ratio of 1 is to 100, means one piece of boron and 100 piece of silicon atoms are being added, then this type of a structure is formed where boron is having three electrons in its outermost shell. It will make three covalent bonds with the neighboring three atoms, and once blank space is left, that particular space is called as a hole. And since it requires a electron, that is why it is called as an acceptor ion. It is going to accept the electron. That is why it is called as an acceptor ion, right? And there are few more things which are to be taken into notice. Due to the absence of electron over here, this whole ion is going to have a positive charge, right? So whenever we are going to connect it to yeah, this is what I have told you. The absence of an electron creates the effect of a positive charge. Hence the name p type. Holes can conduct current. A hole happily accepts electron and goes on. Right. So when we will see the same crystal as I have told you, that when it is attached to a polarity, then the passing of current, the flow of current is due to this holes, positive holes. Right. So that is why it is called as P type of a semiconductor. Right. The holes can conduct current, and a hole happily accept a electron from a neighbor and moving the hole over a space. P-type silicon is a good conductor of electricity, right? Sorry. So a small amount of impurity will give you millions of holes, right? So it is a good conductor of electric heat and electricity. So this was P-type, and for N-type, pentavalent impurity is added. I will let you know everything. When a pentavalent impurity is added, pentavalent impurity means which is having 5 electrons in its outermost shell, right? So when it is having 5 electrons in its outermost shell, and when such type of atoms are added to a pure intrinsic semiconductor, then what happens? So we are working on this group 5 elements uh, where it is having 5 electrons in its outermost shell. So this is nitrogen, phosphor, arsenide, antimony, then bismuth. These all are group 5 elements, meaning that they are having 5 electrons in their outermost shell, right? So when such type of a impurity, that is pentavalent impurity, is added again in the ratio 1 is to 100, means one of Sb and one of antimony and 100 of silicon, right? So when such type of a impurity is added to a pure intrinsic semiconductor, then the 4 electrons in its outermost shell will make 4 covalent bonds, and one extra electron is left for bonding. That particular electron is in excess. Therefore, this whole ion is now going to have the negative charge, right? Because of this excess of electron. Okay, so and if you attach this to the say power supply, then the current will flow due to this excess of electron, and therefore it is called as like N type of a semiconductor. Means the flow of current is due to the negative electrons, and therefore it is called as N type semiconductor. So we are having two types of semiconductors. One is intrinsic semiconductor and extrinsic semiconductor. Intrinsic semiconductor in its pure form is called as intrinsic. A semiconductor in its pure form is called as intrinsic semiconductor, whereas when a certain amount of impurity is added to a pure intrinsic semiconductor, then it becomes extrinsic semiconductor. Right? So extrinsic semiconductor is a impure form. So we are having two types of extrinsic semiconductor. One is P-type semiconductor, and the second one is the N-type semiconductor. Now for P-type of a semiconductor, sorry, I'm going to tell you the statements, right? So in P type of a semiconductor, when a trivalent impurity is added to a pure intrinsic semiconductor, then what happens? The 3 electrons in its outermost shell will make 3 covalent bonds with the neighboring atoms, and one blank space is left over there. That positive, the absence of an electron gives the concept of a hole, that is a hole, and due to which the whole ion will have a positive polarity. If you attach this crystal to a power source, energy source, then the current flow is due to the movement of this positive hole, and therefore it is called as P type of a semiconductor. Whereas in N type of a semiconductor, just listen it very carefully. This is how we are expecting you to write. So whenever a trivalent impurity is added to a pure intrinsic semiconductor, the whenever a trivalent impurity is added to a pure intrinsic semiconductor, the 4 electrons in its outermost shell will make 4 covalent bonds with the neighboring atom, and one excess of electron is left, due to which the whole ion is going to possess a negative polarity. If you attach this crystal to the power supply, then the flow of current is due to this excess of negative electrons, and that is why it is called as N type of a semiconductor. Okay, so phosphor arsenics each have 5 outer electrons, so they are out of place when they get into the silicon lattice. The fifth electron has nothing to bond to, so it's free and move around. So this is how it goes for conduction and valence band. So electrons are free for movement. It takes only very small quantity and the impurity creates enough free electrons. I have told you that for a small addition of an impurity, there will be million of electrons, free electrons, uh, free electrons present for conduction. Okay, electrons have negatively charged, hence the name n-type electron. So this is how it goes. Uh, yeah, so now when we add, so this is the advanced version of n-type and p-type semiconductor. So I guess this we will study in the next class, right? So that is called as p-n junction diode. So I'm going to teach you this in the next class. So this is all about the semiconductors, intrinsic and extrinsic semiconductors. Then these are the band theory. This is how the silicon is there, intrinsic and extrinsic semiconductor. Intrinsic semiconductor means a semiconductor in its pure form. Extrinsic semiconductor means impure form of semiconductor is called as a extrinsic semiconductor. This is the concept of doping. Adding of an impurity is called as doping. P-type for P-type semiconductor, trivalent impurity is added. For N-type semiconductor, pentavalent impurity is added. Right. So this is trivalent impurity. So trivalent impurity over here are boron, aluminum, gallium, indium, and this is Thathium, right? So they are very difficult to pronounce also. So these group three elements are being added to the pure intrinsic semiconductor. Okay, and this is a p-type semiconductor. This is n-type of a semiconductor. So when a trivalent impurity is added to a free pure intrinsic semiconductor, then it becomes extrinsic semiconductor. Okay, I will stop a class over here. I guess if you have any questions, you can ask me on that. So only 1 minute are left.
Expensive semiconductor.
क्या बेटा क्या नहीं समझे once again come again.
Sir, expensive semiconductor.
एक्सट्रिंसिक सेमीकंडक्टर बेटा जो इम्प्योर सेमीकंडक्टर होता है, इम्प्योर बोले तो कुछ और इम्प्योरिटी अगर हमने प्योर सेमीकंडक्टर में ऐड किए तो वो एक्सट्रिंसिक सेमीकंडक्टर बनता है. ठीक है, ये मैं आपको कल फिर से एक्सप्लेन करूंगा. लास्ट 1 minute इज लेफ्ट. Thank you very much for joining. I will continue this tomorrow also. Okay, please join. Have a nice time. Stay home, stay safe, and take care. Bye. Good day. See you soon in the next class. Hello. Okay. Bye. Good day.